I'm gonna be an influencer, I gotta post videos. Just wait for that $1 million contract. Fire Island Concert 2. The Remedy. All right, so, guess this was problem 69, I believe.
Yes.
So something like this, when it's launched and it lands at the same level, there's a range formula, which I really don't care for, so I'm going to ignore that. So there might be some shortcuts that might be of some interest, but we can find the various components here. We're trying to find, I think, the angle at which it was launched. All right. And coincidentally, this is twice the range. So if this is some range here, this is 2 times that. So let's figure out what we know. We got the big phi, we have displacement, we have initial velocity, final velocity, acceleration, and time. So let's just treat through the top here. We have horizontal and vertical parts to it. So vertically, well, that's what they give us, that's 354 meters. Horizontally, well, it's half that because I'm only looking to the peak, so it's half of that. So doing the fancy math here, that is 88.5, I believe. My acceleration here, we'll assume that this takes place on Earth. Now, when I wrote positive, when I have a positive number here, right at that point, I am making up positive, and this is positive, so I'm making that positive, but I should be more explicit here. Before. So I'll make that my I and J directions. I hat and J hat. Meters per second squared, and 0 meters per second squared. This is going to be V cosine theta and V sine theta. This is 0. Because we're taking it to the height, I know 3 things here, so I have everything I need to know to figure out, I can figure this out, I can figure that out. So let's go ahead and do that. What equation, let's find time, what the heck? What equation would I use to find time?
Changing that is equal to,
Yeah. Sorry, which one?
changing x, or this displacement 1, VIT plus 1, or
Okay.
minus 1 half AT squared.
So if we plug in, we don't know VI or T here. We probably know enough.
Could you take the arctan to find the angle?
Arctan of what?
The vertical over horizontal?
Except of that over that?
No, arctan of the height and distance.
Of that, oh, no, because the thing travels in an arc, and this is a mistake I see way too often. If I could just do an arctan of that divided by that, that assumes that this thing is traveling in a straight line, which it's not. It's being launched at higher, and the gravitational pull pulls it down, and so it's going to travel in an arc. So we need to find that angle, not that direct angle. Now, I started out trying to find time here. That was not actually, I don't think that's necessarily going to be the simplest way of doing it. If we plugged into here, we have 354 is equal to V T sine theta minus 4.9 T squared. So I have 2 unknowns.
Oh wait, distance equal to rate times time. Then you manipulate for time.
Distance is equal to rate times time. That works if acceleration is 0. So we could do that over here, which is basically plugging it into the same formula with acceleration 0. We get displacement is velocity times time. So let's do that. So I also have, flipping the horizontal end, 88.5 is equal to VT cosine theta.
If you then solve for v, you can then sub that in into the first one. You can cancel out your t's, and then you can get a, I think you can get a value for v that way.
We have three unknowns here, I think, did I say two earlier? Because we don't know VT or theta.
Oh, okay.
We're gonna need a third equation somehow.
Right.
So upon reflection, I think actually finding what V sine theta equals would probably be good. So what equation do we have that doesn't involve time?
Final velocity squared equals initial velocity squared plus 2 times acceleration times change in displacement.
Let's nitpick. What did she say that is questionable?
Sorry, change in position. Displacement.
Okay, just displacement, not change in displacement? Okay, so that's one thing. Change in position or displacement. As in displacement is the code word for change in position. The other thing, there's one other thing. She started out with something that is questionable.
Fine.
Final velocity squared,
What's being squared?
the final velocity.
The velocity at the peak.
No, not that. It's not.
that.
How would I write the formula? Oh, sorry.
Is v
The
squared,
velocity right before.
No, not that it.
the formula is v squared is equal to v naught squared plus 2a delta x.
All right. So how would I write that?
I just did, you want my final question?
That's missing some stuff.
Yeah,
Is it?
what did I say?
She said it like
Final
the right way,
velocity.
I was listening, VF squared, VI squared.
Oh yeah. Okay. So VF squared equals VI squared plus 2a delta s. I think that's what Aristotle has written on her card.
Are you getting at
That's
others,
what
they're
I
not
said.
vectors?
There's the key. So what are vectors? Which ones are vectors?
Well, basically everything we have.
No.
Acceleration's a vector,
Yes.
displacement's a vector.
Yes. And therefore, since I have two vectors multiplying, what kind of multiplication is it? Yes. All right. What about these?
Cross
Those
product.
are,
A dot.
It's a dot product with itself.
unscalars,
Therefore, what is this?
Speed.
speed. Oh,
I told you I was
okay.
nitpicking. It's speed.
Okay, yeah, I see that.
Now, and this is where you can get, it gets fuzzy because if you square a vector, does that automatically imply that you're doing a dot product with itself and therefore velocity squared and speed squared are the same thing? And that's a fuzzy area that I flip back and forth on. But all right, so we're taking a look at this equation right here. So we got my v sine, so we have 0 squared is equal to v sine theta squared plus 2 times negative 9.8 times 354. So I can solve for v sine theta. And that would be the square root of whatever that is.
Would v sine theta be negative?
Depends on what.
It depends on how we're gonna do it. I figured we'll multiply this all together, this is negative, and then we'll add it to the other side.
That would be negative 6,009.
6,000.
938.4.
All right. And so therefore, that's before you take the square root.
83.297.
83.297.
297.
Alright. So we now know what v sine theta is. So we can now solve for time. So this whole thing, we don't know what v is, we don't know what theta is, but we know the whole thing is 83.297 meters per second, unless there's an error somewhere. Anyone backing Austin up on this? They just had such faith in you. Same thing?
That's what I got with that, yeah.
Okay. So now if we plug into the first equation that, like Mario suggested, we have 354 is equal to 83.297 t minus 4.9 t squared. We can now solve for time. How?
Quadratic formula.
All right. So 4.9 t squared minus 83.297 t plus 354 equals 0. Please don't forget to set the whole thing equal to 0 before plugging into the formula. 3.297 plus or minus the square root of, I think that squared is what's around 6,938.4. Minus 4 times 4.9 times 354 divided by
9.8.
Actually, isn't that, no, it's not.
It is.
Zero.
0.
Zero.
Square root is 0.
Yeah.
All right,
We need to square root of zero.
okay. So we get 83.297 divided by 9.8. Yeah, 0 makes sense, because,
41,
say it again?
10.41. Wait, no, sorry, divided by the wrong thing.
8.499.
Yeah.
The time, seconds.
Seconds.
All right, so 8.5 seconds to get to the peak. We now know time. We can solve for v cosine theta now, because we have this value right here, 8.5. And plug it into the, well, we got it right here. So v cosine theta is equal to 88.5 divided by 8.5, which is 10 point something.
41.
10.41 meters per second. So we now have the initial velocity. Given my coordinate system there, my initial velocity is 10.41 meters per second I hat plus 83.297 meters per second j hat. Now, it doesn't answer the question, but if I had said, what is the velocity? That is an answer that is acceptable. Seems like on the master set, when I ask for a velocity, he will give me speed. So, if I just say, what is the velocity, initial velocity, done. I mean, you can stop it right there. Don't forget, you do need to define I hat and j hat. But they asked specifically for the angle, so now we can do the arctan stuff. 10.41 this way, 83.297 that way. That's the angle that I believe the question is asking. And so theta is the arctan. 82.9?
degrees.
So if you get stuck, just start plugging into the formulas and see if something happens to pop out of it. Oh, I did give the range formula and the Rmax formula.
So you said like whenever you ask for velocity, we have to like split it up into like I hat and J hat?
No, what I'm expecting, if I ask for velocity, since velocity is a vector term, I need magnitude and direction. If you express it like this is known as rectangular form, this is an acceptable form. Or you could be more explicit, if we did Pythagorean theorem here, I'm just gonna pretend the answer is 85, if we did that bit. So if that's 85, you could also express it in polar form, which would then be 85 meters per second and 82.9 degrees. Or, whatever that number actually is. So both would be acceptable answers. If I ask for what is the speed, then I'm looking for, the hypotenuse here. Questions about this one? Other questions? Courtney, Roberto, Jesse. All right. The complex figures problem, and they regretted it. So if I had a propagation of error problem on there, I'd go, let's do something more interesting than just the plain old boring stuff.
Do the master sets count as test grades, quiz grades?
Quiz grades.
Quiz grades.
Yeah, so each quiz has, so all the master sets and all the chapter quizzes, each quiz has not a whole lot of impact. No individual quiz has much impact. Any other questions? And I highly recommend you look at the old tests that are posted on our course documents, and then old tests. All right. I figure one of the reasons why you didn't ask many questions right now is the fact that you're enticed by the box on ramp problem.
Yes.
Let me give you a context of what we're working on, and actually, because this thing has shut off on me so many times, just double checking. I think it's actually oriented correctly, but we'll find out later. The process that I'm taking you through, if you've done physics before, you probably learned certain shortcuts or you have some intuitive sense potentially. I'm going to teach a particular method, and then as you get more comfortable with it, you can start taking liberties and start taking shortcuts. I would like you not to do that yet, even if you've had physics already. One of the advantages of the technique I'm taking you through is it allows you to handle more complex problems than the typical ones. But over time, eventually came up with a mnemonic facades with an extra S. Where the first step, this F is the force diagram, which is one of the reasons why we're going through the force diagrams. Force diagrams will stay with us even after we get into other techniques for solving. A stands for acceleration, direction. The CA go together for the coordinate axes. Because picking the right coordinate axis or coordinate system will really greatly reduce the amount of math you have to do. And so as you get into more advanced math, there is a bit of time that is spent trying to find an optimal coordinate axis or coordinate system so that you really reduce the amount of math. Because don't forget, physics was developed pre-computers, and so whatever shortcuts that they could learn or figure out, the better, and we are still maintaining that tradition. D is for decomposition. When you add two vectors, you get a resultant. When you take a resultant and break it down into two perpendicular components, that's what I'm calling decomposition. E is for the equations of motion. So we're going to come up with our equations for using to solve primarily acceleration based upon the template of F equals ma, Newton's second law. The fact that the total force is equal to mass times acceleration. The equations of motion is not a reference to the cake formulas and similar. It's a reference to F equals ma. S for substitution. This is when you substitute into the equations of motion formulas that are always going to be true, such as there is a formula for weight that we would plug in if weight shows up in the equations of motion. There's formulas for friction. Those are the two main ones we start with. And then the last one is solve. So we're right now concentrating on just the force diagrams, and then once we get that down, we'll start doing problems where we'll go one through the whole thing. It's not like we're going to spend a day on force diagrams and a day on acceleration, direction, and so forth. It's a day on force diagrams, and then we'll do everything. Now, I am trying to make the ramp here part of the ground in this particular case. And so when I draw them as separate objects in preparation for doing the force diagram, I draw the box and then I draw my earthen ramp, planetary ramp. Put down my checklist. All right. So somebody tell me one force acting on some object.
Gravity.
What's the name of the force?
Weight.
Yes, I'll go with that. Or force due to gravity. Gravity is a really huge topic, and so I'm going to start nitpicking people who say gravity is when they mean something more specific. Because there are going to be three things that students will call gravity: force due to gravity or weight, acceleration due to gravity, and the gravitational constant. These are all things that students will just lump under the one word gravity. And so we do need to be a little bit more specific here.
What is the gravitational constant?
Yes, and what is the number, or what does it mean?
Will we use that in this class?
Yes, we will. In chapter 7, I think. It basically allows you to get to the right unit system. It used to be called the universal gravitational constant, and then at some point someone had the idea of, wait a second, how do we know it's universal? We know what it is here. All right, so wait, back to Marisol. Weights acting which way on what?
It's acting up from the ground towards the box.
Up, on the ground?
Yes.
On the ground, okay. All right, so I got weight here.
And then I think the weight of the box is also pulling on the ground, so it's.
No, this is the weight that the box is pulling.
There's one that goes down through the box also.
Down
Through the box?
through, okay. I guess I'd accept that. On the box is the only way my mind's working. All right, so we have this weight down on the box. There's something pulling on the box. And the box is pulling up on the earth. All right, so we got weight. Since there's the planet and one small object, that's it. All right. Can we get rid of anything?
Other,
Okay,
tension,
those are the two. All right, let's do normal next. Which way is normal force acting on what?
So it's perpendicular
Okay,
to the rail.
it's going that way
Yeah.
on the ramp? And they come in pairs, where's the other one? Acting. Normal force is pushing away, keeps one object from going through the other. We are assuming that the ramp has enough integrity that the box is not going to basically grind itself into the ramp. And we assume the box is not going to come off the ramp as it float in the air. Since I have only, that's the only contact I have, there's normal force done. Friction.
Up the ramp, right?
Acting on,
The box.
like that.
Yes. The opposite direction. Right.
On,
On the ramp.
yeah. There we go. So when you're doing the lab, this becomes rather important.
why wouldn't it be like backwards? Why wouldn't the force on the box be pointing down that way?
The friction?
Yeah, the friction.
Friction opposes the relative motion. The box, I mean, if you want to put a box on the ramp, which way is the box going to go?
Down.
Yeah, and friction opposes that. Friction can help movement, but not in this case. All right, let's do box on ramp on ground. And I'll just go ahead and draw the separate objects here. I should give myself more space. So now we have the ramp as a separate entity.
So what's the difference between the two? Like, what's the difference between this and this when it comes to like solving problems? Like, how will you word it?
All right,
How will you know which one to use?
so usually the ramp is assumed it is not going to move. In which case, if the ramp is definitely not going to move, we can assume that the ramp is part of the ground. And so it simplifies what we have to consider. In this case right here, we're going to have additional forces involved. And we'll do an example when we're done, just to show how complex it could be if we separate the ramp.
Is there gonna be a question like on the next test of the quiz about how to word, like which way the force is acting?
Won't be on test 1A, but test 1B, there will be a complex force diagram where you will have to be able to draw the arrows in the right direction.
But not like, say, like write out the direction.
There is one problem that, I don't know if I've done on a 251 test, I think I have, where when we talk about Newton's third law, you'll see what I'm talking about at that point.
Okay.
I think some of the confusion that he has ties into some of what I have. I also get a little bit, confused about the kind of phraseology that you use as far as what acting on what and what, in, on, through, those kinds of words, which indicator words, mean what when you're talking about these things.
I try to use on, probably not 100% on doing that, but I try to use on when I'm doing it because that tells me how to draw the arrow. I'm drawing the arrow on an object in a particular direction. The reason why I have issues with some of the language that I'm hearing is that, for instance, right here, this force right here is from the box.
Right.
This is from the ground. This is on the ground, but from the box. And so that's, and I know when the student says, oftentimes they'll say, you're drawing it from the ground, they're thinking of, this is a starting point and you're drawing it. But from a physics point of view, from implies, the source. Yes.
Okay.
And that's where I'm trying to work on the language.
Okay.
So would it be like the weight of the ground acting on the box? Or do I have it backwards?
The trouble with weight on, you said weight of the ground?
Yeah.
So it'd be weight of the box.
This is the weight of the box acting on the ground.
Right.
The weight of the box acting on the box.
Acting on the box.
Wait.
No, from the box.
Well, when you talk about weight, it's difficult really to talk about the weight of a planet. The weight of the ground, because the ground has mass, but really to have weight, if we crash into the sun just before we, hit that, whatever the outer surface is, you probably could talk about the weight of the earth at that point, but otherwise, weight of the earth really doesn't make any sense. And so, and I'm equating earth and ground as being the same thing. So that's, again, some of the language. In terms of a test, I think, not necessarily addressing what Max's concern was, but related to Max's question, I don't think there's any test where I'm nitpicking the language like that. I reserve the nitpicking for face-to-face. Because I want to treat you like family. I used to nitpick my wife's grammar. I was shocked to find out that not every family picks on grammar. I guess that's what happens when your dad's an English teacher and your wife's dad was not. Are there any, I think we've addressed the questions, but it's possible that we've just opened up more, or I didn't quite address any of the questions. All right. So, all right, so we now have the three objects. We have our checklist also. So give me a force and an object and a direction. I keep alluding to you, Marisol, because you started off last time. She doesn't have to be the one who starts us off.
The weight from the ground, to the ramp.
From the ground to the ramp. All right, so I'm drawing my arrow on which object?
Up on the ground, up from the ground. And then
Okay.
that's gonna be weight 1. And then there's one from the ramp, on the ramp to the ground, and that'll be weight 1 also. Then there's a weight also acted on the box to the ground.
All right, toward the ground. If you say to the ground, I'm thinking all the way down like that, just in that direction.
Towards the ground, that'll be weight 2. And there's one on the ground acting up on, towards the box, and that'll be weight 2.
All right. Since I have only two small objects besides the planet, and weight on the small objects will always be down, because that's how down is defined.
So you're not gonna have tension in this one.
Correct. So get rid of that.
Another.
There is no other. There can be only one.
There's friction acting that way on the box. And it's acting the opposite way on the ramp. I think there's also natural, normal, sorry, normal tension.
Let's just throw it.
I mean, not normal tension. I get nervous when I put on the spot, I'll let somebody else go.
The spirit of what you're saying is right so far. So there's normal force acting on, do you want to pass it on to someone else?
I'm passing it on, yeah.
Okay.
I mean, I know it, but I feel like I'm dominating it. So
Okay.
I'll just pass it
That's-
on.
It's nice of you to share.
Normal force acting on the box away from the ramp.
Good.
And then normal force acting on the ramp away from the box.
Would we want to, subscript that one, since there will also be the normal force between the,
Do you want to?
sure, I just wonder what the usual convention is, maybe on that, just like one.
All right, so in terms of subscripts here, these two weights need to be the same symbol, and these two need to be the same.
Okay.
So I could have gotten away with no subscript on one of the pairs, but I can't get away with no subscript on any of them.
Right,
So, generally, subscripts are your friend.
so we could just put one and that's cool.
You could put one here if you want.
Okay.
Well, that's what you said, so we'll go with that. I would have gone with
I
two,
would
just because
have
that's
not
already
wanted
marked as
to do
two.
that. Okay, alright, well then two, it doesn't matter.
Or probably would have done B for box, but,
And then there would be a normal force between, so acting up on the ramp. And that would be normal force two. And then down on the ground, also normal force two. Would there be friction between, well, that requires relative.
desired, really.
Okay.
So,
Never mind.
does the ramp want to move?
Doubt it.
Hey, a ramp. What a mass, it's not gonna tip over. Oh, wait, here we go. Mass and ramp. So when I put this on the wood block and let go, is the wood block going to move?
Yes.
Which way is the wood block gonna move?
Last relative.
I, going with the spirit of what you were saying. Whoa, it moved. So the ramp wants to shoot out that way,
So friction is going up
acting on,
the ramp. And then there's one on the ground going that way.
Friction two.
there we go.
This one, friction two.
And I would not take off word if you did not put a subscript here and here, just because, I mean, that is different than those. It's clear that that's friction and that's friction, it's clear that those go together, and those go together. But if you want subscripts, oh, why not three? Doesn't, as long as it's not two, because that F sub two has already been done. And some will go A, B, C, and just do subscript to letters. I don't think anyone's done subscript Greek letters yet.
So when you say desired, relative, motion, I mean, clearly if you just throw a smaller, mass on the ramp, it won't move.
Right.
So how do I know when I need to be
The-
including that and when I don't.
If this, the way I do it is I imagine if this were frictionless,
Okay.
would it move? And so that triggers, okay, if it would move, if it's frictionless, then there's desired motion.
Okay.
Just like putting a block, just putting this onto the ramp, we don't know whether it's actually going to move or not. I can put an object on a ramp and it not move. There's lots of objects not moving there. So, but if it were frictionless, that stuff would go sliding. And there will be situations where you're going, I'm not sure, in which case you assume worst case scenario and then figure out later whether it is or not. Those are horrible, horrible problems. So I'll try not to subject you to too many.
Thank you.
You got it. All right, any questions at this point? We're gonna come back to box on ramp because it does relate more directly to the lab that you did last week.
So was that all of them?
Is that all of them?
All the forces?
No, we haven't
No,
done tension yet.
Yeah. Is that all the forces?
And there are other forces that we're gonna add as the semester progresses. Box A, box B. Blocks dangling from rope attached to another object on, at this point, I sort of run out of the easy descriptions. So something like this, there are a couple of assumptions we're going to start out making on this that we can do away with later, but for right now, this is going to be an ideal rope. Ideal rope has three characteristics. Ideal rope is massless. It is frictionless. And we assume it's somehow magically attached to the box. And it is stretchless. The frictionless aspect we will do away with when we get into rotational motion. The massless aspect we may or might not do away with. 251, you definitely can handle it if I throw mass into the rope. And stretchless, we're going to keep for the rest of this course. If it's stretched, then it's a possibility that B can start moving and A hasn't moved yet. And so that's one of the situations I want to not deal with. The pulley is also ideal. And the ideal pulley is massless. And frictionless bearings. So as it's spinning, it's not losing any energy on the spin. We will give it mass when we get to the rotational motion. And there are some problems where at the bearing here it's frictionless and some problems where it's not. I mean, you'll be able to handle that by the time we get there. But we're going to start out, at least until chapter 10, whenever the rotational motion starts. We're going to assume ideal. Now, as you're reading if you look at test 1B, I think every rope in there is ideal. I didn't necessarily state it explicitly because, well, I knew what I meant. But if you're ever not sure, just ask. So one of the questions, if I just said, hey, do a force diagram for this one of the questions that a lot of students seem to have is, do I treat the pulley as separate or not? Well, a lot of that depends upon the problem. At this point, since the pulley's not really moving, there's nothing to cause the pulley to move because we have a frictionless rope going over this massless object. There's nothing to make it move. And so it's, I could just as easily have drawn this cliff here with, a part of it jutting outwards. So the pulley is part of the ground. Now, on the complex force diagram problem, which we have not done one yet, but on the complex force diagram problem, I separate it for you just so you don't have to worry about, is this part of that or not? Although some students will still treat the pulley as separate, even though I draw it attached. And then we have box A, we have rope, and box B. So here, it should be clear that the pulley is part of the ground, because I've drawn it part of the ground. If, on a test, on the complex problem, you decide to do the forces between the pulley and the ground, I generally circle them and write something that looks kind of like IGN for ignore. It's known as an internal force. If you're gonna look at the force between the pulley and the ground, why not do the forces between the top part of the box and the bottom part of the box? And there are all sorts of additional forces you can throw in there if you start looking at the internal forces. All right, our checklist. And since tension is the new one, let's do that one last. Can we get rid of anything?
Other.
All right, and we're off. So Marisol's gonna start you out again?
Restriction acting against the box, going that way from the ground.
From the ground against the, don't you it? Okay. Give me fair. What's the other part?
On the ground, going that way.
There's weight on A going down. And then on the ground up.
Yep. Now, where you draw it on the ground, since this whole complex here is considered the ground, it really doesn't make a huge difference if you draw it here, here, wherever you draw it. I try to align it with where the other one is, but not required. Some students will just put a whole bunch of arrows down here. If I've got 6 objects all with weight, they'll just put 6 arrows in a row and just label each of them. Okay. On a roll, got 2 down.
So normal force on A. And
Going which way on A?
going down.
Look at it. What's holding the box up?
Oh, it'll be going up.
Yeah.
Yeah.
Normal force pushes away. All right, so we got that one there, and
And there, normal force pushing down on the ground.
3 down. And 1, 2, 3, 4 to go. 4 more pairs.
There's gonna be the force of the weighted box B pulling towards the ground. And there will be a corresponding force pushing up towards box B.
Okay. Since those are the rope doesn't have any mass, so there's no weight there. So we're done with that. Friction, yeah, that's the only friction, with other friction.
Is there a normal force between the box and the rope? Or either of the boxes and the rope itself?
No. Now, the rope is somehow attached to the box, but we don't know how it's attached. I didn't give that level of detail. So we're actually not quite sure what kind of force it is. It could be that if the rope is sort of wedged in there, then there's friction. If I have an eye hook attached and it's tied to the eye hook, then it's a normal force. So since we don't know, we're gonna call that tension.
So are we then done with normal forces?
We are not.
We're not.
Is there a normal force between the rope and the ground?
Ooh.
No.
Oh,
The pulley's part of the ground.
Yes, yes it is. I apologize, yes. Now, I know the rope touches the pulley from here to here. So the normal force has to be somewhere in that range. Normal force requires contact. without more information, we don't know exactly where the total normal force is, and so I just some generic direction. Since it's our second normal force, we need to do something. B? Okay. And then the other one's just in the opposite direction, acting on the ground. All right, so normal force is done. Those are the only points of contact we have, and so now tension. Remember, tension pulls. It is pulling on the ends of the rope. So we have a tension pulling this way. Where's the other part of that pair?
On the box to the right.
On the box towards the rope?
Yeah.
And I think that's what your hand gesture was. So that is the one tension pair. And I know I've got another tension pair at the other end. And that's a tension pair. Each end of the rope cannot be part of the pair as we're talking about it, because, well, they're not in opposite directions. Pair forces in the pair always are in opposite directions. As well as this is not a force exerted on the rope by the rope itself. Now, if you're doing subscripts, if you're doing the subscripts, these two have to have the same subscript. And these two have to have the same subscript. However, if the rope is ideal, then the tension throughout it is actually the same. So the subscript is optional if it's an ideal rope.
So for problems, we're just always gonna assume that it's ideal unless otherwise specified?
Until we get to rotational motion, that's probably pretty safe. Unless I state explicitly otherwise. But once we start getting into pulling rotating, then the tensions have to be different because if you've had physics before, then you might be familiar with torque. They're torque applied by the tensions. If you haven't had physics before, then you'll be introduced to something known as torque. Or in my classes, G2 Kabuka. But we'll talk about that later. So we are done. I assume you're about to take a picture.
Yeah. I don't have Facebook, but I will create one.
The Carol Merrill impression. Watch enough prices right. Yeah. You know who Carol Merrill is?
I do now.
All right, we're gonna do one more of these smaller ones, and then you'll get to see a test level problem, and then we'll actually get into solving it. Anybody still writing this down? Please don't confuse my sloppy drawing with something that's very special. Both boxes are touching the ramp. I'm treating the box and the ground as one thing, and the pulley. So let's draw that. So I've got one object. A I want to do friction last. All right. you're saying?
There's also another one from v01.
I do want to point out, if we did have a second rope, we would have to use subscripts. That one rope would have one set of subscripts, and the other rope would have a separate set of subscripts, even if it's ideal. All right, so tension's done. We have one rope, and we've taken care of both ends.
Oh, wait, you said you wanted to tension last.
Friction last, it said friction last.
Oh, okay.
Yep, no, we're good. I would have stopped you if I'd said tension. Can we get rid of anything?
Other?
Yeah. Can't always get rid of other. Now what?
I'm just trying to, and I see so well because the glucose is.
So we need to,
From box B, backing down on the ground, and then from box B going down.
not down on the ground,
Yeah.
down on B.
Then up on the ground.
On
Why
the
did I say that? What's the proper vocabulary?
This is the weight acting up on the ground.
And then,
This is the weight, this is the force from the ground, this is the force on the ground. That's why when people use from, I have to do a double take of, all right, what do they mean here? And then, I'll spoil it, similar one for A, got A acting down. So we do weight. And since the rope is massless, there's no gravitational aspects, no gravitational pull on it.
I'll go force on the pulley, away from the pulley.
Away from the pulley, so
Yeah.
where am I drawing my arrow?
On the that little circle thing, away from it.
So I'm drawing,
It would be a normal force on the rope away from the pulley.
okay, is that what you're saying?
I guess.
Is that what you're saying?
Yeah. and then
Okay.
down there.
Normal force on y sub r, y sub r. And again, I don't know the exact direction of y sub r, depends on other factors that are not mentioned that I didn't give you, but it's somewhere in that general area.
Here's normal force on box A up. Yeah,
Perpendicular.
well, like that.
Yeah.
And then it's going that way. on the ground.
I wasn't looking, but I assume that's what you meant.
Yes,
Okay. And
also on B.
And even though I'm not modeling it in class, please make sure I can read your handwriting on test.
I have a question.
Yes, ma'am.
If you draw the WA on the ramp, does that make a difference?
No.
Or no.
That's
So you
fine.
can draw it on the ramp.
Yes, yes, you could.
And
Because
it's
this is
pointing-
all one object, so it really doesn't
It's
matter.
pointing up on the ramp.
And which,
It's just pointing up on the ramp if you would draw
yeah,
it.
it's pointing upwards, technically from the planet,
Yeah.
but if we follow this in a direct line, it should go right to the center of the planet. Center of gravity of the planet. All right, friction.
Acting on box A parallel to the planet.
But you don't know which direction. Depends on which one's heavier, I guess.
And that part of it, it depends on two things. What are the masses of the two objects and what are the angles? Because we have an angle here and an angle here, and I didn't tell you either of that, I didn't tell you the masses. And we really need to know both angles and both masses in order to be able to know which way it's gonna go. So one of the reasons why I wanted to do friction last is because I did not give you enough information. So I'm just going to tell you, assume it's gonna go this way. Assume that the velocity is, A is gonna go up, B is gonna go down. Therefore,
Friction on box A going down. And from the ground going up. That'll be that pair. And on box B, friction going up in the box and friction on the ground going down.
all right. So we've now laid the groundwork for doing a test level problem. Do we need to rearrange some chairs so you can sit closer?
It's just today, because the thing is impaired. It's okay.
Go ahead. Go ahead. Chair, here if you need. There's a chair.
Thank you, George.
Do we need to rearrange anything else? Because, I guess Marisol and Precious, he's closer to you than,
Yeah,
are you good or do you want to move?
I can move there.
Okay. And I guess Marisol, you're second closest. Sure, okay.
Here we go. So since the whole ramp and everything is part of the ground, like the friction, can it like, you have it facing from like the left to the right on the horizontal part of it? Or does it have to be like diagonal part of it, like compared to the?
I mean, the direction of the friction?
Yeah, like, can you do it from the ground, like have it be like horizontal, going like from left to right?
Oh, down here, going this way?
Yeah, would that
No,
be the same?
because the friction has to happen where the contact's occurring. And so it's occurring, and it's also parallel to the surfaces. So it really has to be along that line. Did it answer your question?
Yeah.
Okay. Other questions before I erase this? All right, so I will draw the test level problem.
What is the normal R?
Because there's a normal force between the rope and the pulley.
But R,
I did R for rope.
row.
Sometimes I do P for pulley. I'm in an R mood. Now, I originally designed this to be dad pulling boy on sled. Dad's actually pulling the sled, not the boy. And it's a dad and a boy because, well, I wrote the problem and I was thinking of my son. Feel free to change that. I guess it could be Sinead O'Connor. That would be. It's like a half of an arm there. It's my cousin. My cousin actually was born, have I done the cousin story? He was born with a birth defect, so his arm basically just came slightly past the elbow, and he had the little nubs where the fingers would have been, but this part wasn't there. So there was a point where he was sort of sucking on the end of, sucking on the nub when he was younger, and this kindly woman came up to him and just jokingly said, "Better be careful or you'll swallow your hand," at which point he pulls the nub out and his hand is missing. She screams. The parents then explain, no, it's okay. All right, so here we go. We need to draw this separated. All right, so we got ground. I'm gonna have sled, boy, rope, that's supposed to be his hand. Andy, I was blanking on my cousin's name. It's like second cousin, so. And I'm assuming that in your own drawings, you will draw them more lifelike. Go over checklist. On the test-like problems, I think the most number of forces there were about 40 forces. Probably the fewest was 22, something like that. Just to give you some idea of a range. Often inspired by something I watched on TV recently, or something that's happened in my life recently. And then embellished in order to make it a more interesting problem.
Do we have to separate out the components on the test?
On the complex problem, I separated out for you just so that there's no question about what goes with what.
Okay.
All right, here we go.
Friction acting against the slide.
Let's do friction last. I know, big fan of friction here, but let's hold off on just. Friction's the most complex one, so that's why I want to wait. Well,
Get rid of other?
Pardon?
Can you get rid of other?
We can get rid of other, yes.
Tension in the rope.
Yes, there is. You want to guide me through it? You're starting on this end?
Yep, that'll be going down, right? The other direction would be going up.
There would be another pair on the other end of the rope, going towards the father. Yep. Well, no, but along and parallel with the rope. So, yep. And then the other one would be there. Yep.
The biggest mistake I see here is people drawing the arrows between the rope and the hands. And so basically they're drawing it like that because that's how I happen to draw these pictures. No, the problem is, this is the problem. This is, all I've done is just draw the dad and I've drawn the rope here. So do draw the arrows like this. And I'm gonna try to straighten that out just a little bit. Okay. All right, so tension done, because there's only one rope with a problem.
Be the weight of the dad pushing towards the earth.
Say,
Well, being pulled down towards the earth.
so dad's being pulled down towards the earth, okay. So we got gave him a tail. So weight of dad.
And then the other one will be going from geared towards that direction of the arrow. Yep.
Is that what you mean?
Yes.
I make you gun shy here?
Yes, definitely.
There is a problem if it goes up of the line or?
No, so long as it's clear that it's connected, you're associating that force on the earth.
Okay. Then the same with the buoy and the gear.
So weight of boy. Weight of boy.
And then there's the weight of the sled also going down.
Absolutely. Weight of sled. Weight of sled. So I've only 4 objects besides the ground, and we got weight on 3 of them. What about the rope?
If it's an ideal rope, it's massless, so there wouldn't be any weight.
Now, some students will put weight on the rope, and I don't take off for that. It's what again, I'll circle it and write. That's IGN for ignore.
Sure.
Yeah. As long as when I'm grading it, I know what I wrote. All right, so weight is done. Just doing friction last, how about the end?
Normal weight going up from the sled,
Up from the sled?
like from the ground. No,
All right, so wait, I'm drawing this arrow on the ground or on the sled?
on the sled.
On the sled, going up, okay.
And then the other one on the ground going down.
Okay. One down. One pair down.
The normal force of the buoy in the ground, so it'd be the normal force on the buoy going up.
Would it be from the sled to the boy?
Yes, not ground.
That's fine.
I guess B for boy.
Normal force on the dot.
Which way?
Yeah, up. Then on the ground, down.
And I think it's mentioned just last time. This Y sub D down on the ground here, this is what is causing the footprints in the snow. Or, I'm assuming there's snow. Having lived in the South, you can imagine this is just sort of a wishful thinking. All right. Questions up to here before we tackle friction? All right, Mario, you were saying?
Friction acting against the sled.
So here?
Yeah,
Go ahead. All right.
Then the other one's on the ground.
All right, so let's do boy and sled next. Which way is friction acting on the boy?
That way,
Sorry,
backwards.
that way?
Yeah.
Okay. Several people all pointing that way. Kyle, which way were you pointing?
Well, I was just saying, if the sled's moving that way, the friction would have to go that way, wouldn't it?
And which way are you going? You went that way?
Yeah.
So you're saying they're all wrong, that somehow in their childhood, they got messed up. And you're saying you don't know what happened to him. I think you pointed. Do you have an opinion? Roberto, Enrique, and Precious?
I know the father is going that way, then the friction is taking him that way.
All right, so we got another vote for that way. And Enrique, you're going that way? And Precious?
Well, let's,
How many votes for this way?
There's
I
like-
think there's two.
But everyone's saying it that way. Majority rules.
Wait just a second. Something got lightheaded. All right,
I will say this way.
all right, so another vote for that way. Okay, Austin, you were about to say something?
Right, well, if the sled itself was frictionless and the father pulled on it, then would not the son be sliding off the back
Yeah,
of it?
he'd be
so
moving
that it would
backwards,
be-
so the
So
friction would be
friction
going
will
that
be
way.
this way.
So friction is going that way because
If the
the
surface
sled's
of the
getting
sled
pulled
was
forward,
frictionless,
the boy's going
He
backwards,
would
so that means
slide
the
off
friction
the
is
opposite
going this way.
direction.
So let's simulate this absolutely stunning thing. Sled, boy. So the sled's being pulled that way, and so if it's were frictionless, the boy would just basically not move for a while until he falls off the sled. So from the sled's point of view, the boy is traveling backwards. From the point of view of what the boy is touching, the boy is traveling backwards. That's the relative motion, the relative aspect. It's relative to what he's actually touching. And so, friction's acting this way on the boy. There's another way of looking at it, which I want to do the dad next, and then we'll talk about it. All right, here we go. Which way is friction acting on the dad?
What?
Let's actually see physics by democracy works. So this way, or no friction. There's the three choices. All right, so who says it's friction's acting that way on the dad? You seem hesitant. So wait, no, I'm just doing this way right now. 1, 2, you're on 3,
The dad
4,
is moving to the right.
and to the right.
To the right.
I know you've got your vote there. 2,
I vote for that way.
and Austin, did you vote?
No, I'm abstaining on this one. Because I messed up on the last one, so I'm going to wait and see.
And Austin, did you commit?
No.
I just throw you over there. 11 people for no friction. What do we have in the class? Let's see, we got 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9. All right. Whether I counted for everyone or not, that's where we are.
Is he,
All right, so
is the dad stepping or shuffling his?
he's walking.
Yeah.
He's about to take a step. I have only 1 foot on the ground for a reason. All right, so let's think about that. The argument, what's the argument for to the left?
The dad's moving in the opposite direction.
Yeah. I
Okay.
guess I see it. If there was no
He's
friction,
stepping.
he would be sliding
Yeah,
and slipping and
so
falling.
if he's stepping, would it be no friction?
Wait, I think it would be this way, because if there's no friction, his foot would be sliding backwards.
The key is what is actually making contact here. Yeah, the dad is going this way, but the foot is trying to go back. And so we can simulate this. Again, one of those, if you work for DuPont, do not do this. So as he's stepping, think about this piece of paper between my foot. As he steps, my foot is pushing the paper back. So that would be, the foot is pushing the ground backwards. It is indeed to the right, because it is, the foot is the key there. Now recognize, if both feet are on the ground, then it suddenly becomes a little bit trickier, because when a person walks, and we're just gonna have to sort of theater of the mind for some of you. So right now, as I'm pushing forward, friction is acting forward on my back foot right now. When my front foot lands, if this were frictionless, if you've ever walked on ice, you'd know it. my front foot would slip out from underneath me and go forward, so right now there's friction acting backwards on my front foot. Friction, at this point, there's no friction acting on my foot if I'm directly over it, and then friction is now acting forwards on my back foot. Well, actually, when this becomes my back foot. So friction acting on the feet, keep flipping back and forth. The other way of looking at this, I said that acceleration was to the right on purpose. Because there has to be a net force acting in the same direction as acceleration. If this force is acting backwards, if this force is acting to the left, then you have no forces that are accelerating him to the right. Same with the boy. If friction is acting to the left on the boy, you have no forces acting to the right. There's no way that he could be accelerating in that direction. And so that is a test level problem.
Is there any way that you could go over the friction pair between the sled and the boy again? Because I don't know if I missed something there, but I'm still confused as to why the friction acting on the boy.
You actually worded it quite nicely, because the sled's going this way. If we're frictionless, the boy is sliding to the back of the sled.
Okay, all right. Because I actually, when I said that, I said the right thing, but I was meaning something very bad.
Okay.
Okay.
So from a point of view of contact, the boy would, in a frictionless situation, the boy would move to the back of the sled. From a Newton's second law point of view, there has to be some force in the direction of acceleration, and since he's accelerating to the right.
So more generalized, when you take it to an example of if the surface is frictionless, the direction of relative motion is going to be opposite the direction of the force that you're going to want to draw on that particular object.
Yes.
Okay.
So flipping it around, since the boy's moving to the back of the sled's moving to the front of the boy. And so the direction of the friction on the sled is backwards because it's moving to the front of the boy.
Okay.
Are we ready to actually solve a problem? What else do we need to know? So what's the magnitude of acceleration? I'm going to take us through the steps that I'm trying to teach here. This mu equals 0. This is indication that there's no friction. This mu represents the coefficient of friction. So this is just a shorthand to saying no friction. Friction will come. First step. We've already done this one, so I'm just going to zip through what we have already. So weight A, weight B, There's no friction, so that is not there. Now, in a lot of these problems, you can look at it and you know what's going to happen. Which way will box A accelerate?
To the right,
Yep. Which way will box B accelerate?
down.
Yeah. So it's very clear what's gonna happen here. There's no trying to, hey, let's guess and then see if we're right or not. So this is going to accelerate to the right. So I'm just gonna make a notation here. This is not part of the force diagram. This is just I just need to report it somewhere. So acceleration and acceleration. The magnitudes of their two accelerations are the same because the rope is ideal. It will not stretch. As B moves, A moves. So step 2, acceleration direction, done. Coordinate system, we don't need the same coordinate system for both of them. They can each have their own special coordinate system. Strongly recommend, especially if velocity and acceleration are in the same direction, that be one of your coordinates, one of your axes is positive in that direction. Since box A is going to move to the right, I'm going to set up my coordinate system. I'm going to make I hat, and call it IA hat. In the same direction of acceleration, J hat is perpendicular to it. Now, if you want to make J hat positive up or down, it really doesn't matter. Just pick one. Somebody pick one, up or down, positive.
Positive down.
Sit down.
Yeah.
Now box B is going to accelerate downwards. So we're going to set up a coordinate system for B here. And I'm going to just make that I hat B. I hat doesn't have to be in the direction of acceleration, but that's just what I did. It's purple. So the coordinate system, I hat A, J hat A, and then over here, I. Decomposition. When we're looking at decomposition, any questions about the choice of coordinate system? Or how the coordinate axis here or the coordinate here?
Yeah, why your eye is horizontal now is vertical here?
Why not? I need some label. You wanna make it Z or J or?
No, it's not that, it's that for me, in this space, you got a X, let's say X, Y, Z, or I, J, I don't know, the other letter.
Okay.
And that's it, and then in the whole space is encompassed like that, no? Then if you put it I and J like that, I understand it, A for this object and B for this object, but that should be J, B.
All right. One of the reasons why I deliberately put I there is,
the same magnitude there.
well, they're all, these are unit vectors, so they're all magnitude 1.
Okay.
But the reason why I chose I here instead of J is that I'm trying to emphasize that they are separate coordinate systems. Because even though in this case, I could come up with one system that works for both of them.
Okay.
However, if we get into the double ramp problem where this is some angle and that's a different angle, I will choose a coordinate system like that, and I choose a coordinate system like that. These are not, if we chose just one coordinate system will work for both, then we're incredibly increasing the amount of math we have to do. So, I'm just trying to emphasize the fact that these are separate.
Okay.
Even though in this case, we could have gotten away with just one. We will do this kind of problem later. All right. Decomposition. When I ask decomposition, the question is, if I think about the forces that are acting on the object, so I got 2 here and I have 3 here, are there any vectors that are not in the positive or negative I direction or positive or negative j direction? Positive I, positive j, negative j. All of them are either vertical or horizontal, like my axis, like my coordinate system. Here, positive I, negative I. Nothing to decompose. Box on ramp will have to decompose, but nothing to decompose here. So done. Equations of motion. I start out with F equals ma. I'm going to have 3 equations of motion. I'm going to have 2 for this one because this object has forces in 2 different directions. I'm going to have 1 for this one because I have only forces along one line. So I'm going to have an IA. Now some students will put an equal sign after that. It shouldn't be an equal sign from a math point of view. It's just, I'm doing this as a label. I'm going to have a JA equation and IA equation. Oh, sorry, IB equation. We start out with, well, IA is the first one I wrote down, so let's do that one. What are all of the forces in the positive IA direction acting on A?
Tension.
So I write down tension. What are all the forces acting on the negative IA direction? Nothing. Yeah, there's nothing going that way.
Oh, because those are all J hat over here.
Yeah. Equals the mass of A times the acceleration. The acceleration of A, but A and B have the same acceleration, so just times A. First equation of motion, done. Now we go to the J equation. What are all the forces in the positive JA direction? What are all the ones in the negative JA direction? So minus YA equals the mass of A times, what is the acceleration in the J direction? In the JA direction. What's the acceleration in the JA direction?
0.
Precious, say it again.
0.
0. The thing's accelerating to the right. It's not accelerating up or down. I hope not. I hope A is not coming off the ramp or digging into the ramp. Times 0. At some point, we're going to bypass the formality of it and just write equals 0. But vertically, it's an equilibrium. The forces up equal to forces down.
That means those 2 forces cancel each other out?
Yes. So there's no, it's in vertical equilibrium. What is the label on it? And now someone want to take a shot at what's the equation? The last equation. 0 is not an equation.
It'd be the weight of B minus the force of the tension is equal to 0. Well, mass of B, 0. Times 0.
Times A.
Well, times A. Oh, oops.
Yeah, this one, there is acceleration in this vertical direction. There's no acceleration in this vertical direction. These are 2 separate objects connected by, well, tension. Those are the equations of motion. And traditionally on test 1B, there is one complex equations of motion problem where I give you all the forces and the angles and ask you to come up with the equations of motion. I eventually just went too far and made it way too complex, and then I started scaling back. There's 4 students that year. Anyway. Substitution. Now the question is, as I'm looking at this, do I have a formula, a separate formula, independent of the problem for anything? Is there a formula for tension?
No.
So is there a formula for tension?
No.
Is there a formula for mass? Or confidence?
No.
Is there a formula for weight?
Yeah.
What is the formula for weight?
Mass times the force of gravity.
Ooh.
Gravitational acceleration.
There we go.
Acceleration due to gravity.
Gravitational acceleration or acceleration due to gravity, either one. So weight is equal to mg. That is an independent formula that's going to be true. Presumably, I've made the snide comment already that some textbook readers will read it as weight equals milligrams. Anyway, so basically I'm going to take that, and anywhere there's weight, I'm going to pop that in. So my first equation stays the same, so I have tension is equal to mass of A times acceleration. The second equation becomes MAG minus YA equals, may as well just go ahead and write 0. And the third equation, MBG minus tension is equal to MBA. Now I'm trying to solve for A, and it turns out because there's no friction, this middle equation here has absolutely no bearing on the problem at all. This one is ignored. We're at the solving phase. So I'm solving for acceleration, and so I've got this equation here, and this equation here, and I'm just going to add them together. I'm going to add the left sides and add the right sides. Or you could substitute MAA in for tension. But if I add them together, I have a negative tension here, positive tension here. So I have MBG, tensions cancel, equals MAA plus MBA. I'm solving for acceleration, so let's factor that out. So that's equal to MA plus MB times A. Or acceleration equals MBG divided by MA plus MB. And then to actually solve the problem. Let's assume it takes place on Earth. So we have 3 times 9.8 divided by 3 plus 5.
No negative sign? Is it because we defined I
The-
have positive down?
No, the negative's already been taken into account here. Lowercase g is always a positive number. And so that's going to be somewhere around 2.6.
3.675.
Oh, good, sorry. 3.675.
675 meters per second squared.
We've now gone through the first massage process. As we get into different techniques, as we get into energy and momentum techniques, we're still going to start out, force diagram still holds true even as we get to other techniques. But we're not there yet. But we will learn some other tech. When you start bringing the energy and momentum into it, we can skip some of the intermediate stuff. All right, questions before I erase? I guess Lawson, you're still getting stuff down?
Yeah.
All right. I know you've been anticipating it, and now it's time. Box on ramp. theta. Box is part of the ground. So mass of box will make 6 kilograms, mix it up a little bit. And we'll let theta be, let's go with 53 degrees. As always, force diagram. Now in reality, the box, we're trying to find the acceleration of the box.
That's 6.
Pardon?
6 kilograms.
6 kilograms, yes. So the forces actually acting on the ramp are irrelevant to the problem, but we're still going to do it for completeness at this point since we're still in the early phases. We've done box on ramp already, so whatever. Weight acting down, weight acting down. Normal force this way. I'm going to throw friction into my equations right now. We're going to, first time through, we're going to ignore friction, but I still want it in here. So, let's stop doing this part. Why? Which way will the box accelerate?
Down
Yeah. So, coordinate system. Which way should I make I hat or J hat?
I had that way.
And J hat?
Yeah. Yes, that.
That way? No. J hat could be in the opposite direction, it doesn't matter. Just I hat, the one in direction of acceleration is important, the other one, pick one or the other. Coordinate axes, done. Decomposition. Are there any forces that are not in the plus or minus I direction or plus or minus J direction? So we need to break weight up. We need to figure out how much of the weight is down the ramp, how much of the weight is into the ramp. So, let's do a little geometry here. Whenever I'm breaking a vector up, that angle there is theta, whatever I'm breaking up is the hypotenuse of a right triangle. Now, obviously, I haven't drawn the right triangle, drawn it, so that's the right angle yet, or I've not drawn it, so that's the hypotenuse yet, but I'm trying to figure out how much is down the ramp and how much is perpendicular to the ramp. My components need to be in the plus or minus direction of my axes. This is my coordinate system here. I need to break vectors up into those components. So since one of them is down the ramp and one of them is into the ramp, that is a right angle there. So the question is, what is that angle?
That would also be theta.
Why?
Well, because the angle right next to it would be the complement of theta.
Oh, that's theta prime.
And so, since that makes a 90-degree angle, that would have to be theta.
Yep, absolutely. Or that's the complement of theta there. If you look at the bigger triangle. So I'm calling theta prime.
Yeah, the two sides are perpendicular.
So if my hypotenuse is weight, that means that this opposite side to theta involves the sine. This is weight times the sine of theta. The adjacent to theta, this is weight times the cosine of theta. since weight sine theta I hat plus weight cosine theta j hat gives me weight straight down, I can now change my force diagram there. I have normal force still the same direction, friction still the same direction. And I now have down the ramp is W sine theta, into the ramp, W cosine theta. And we'll quickly go to the shortcut of, well, if we're given this angle of the ramp relative to the horizontal, the sine components down the ramp, cosines into the ramp. But that's decomposition, done. How many equations of motion will there be? Is there a question mark at the end of that?
No, it's gonna be two.
Okay. Because Austin said so. Why do you say it's two?
Because you only have the one object that you have to figure out in the I hat or J hat directions.
Newton's second law is my model, F equals ma. Got my I hat and my J hat equations. So what's the I hat equation?
W sine theta.
Minus friction?
Is equal to mass of the box times acceleration.
Now, I did put a subscript over there of box, but considering there's only one object, I don't feel a need to, but nothing wrong if you put the right box as a subscript. All right, what's the other equation?
W cosine theta?
Minus normal force. Equal limit.
Zero.
Why zero?
There's no acceleration in the J hat direction.
Right. Yeah, if you put A there, suddenly this thing is accelerating, not accelerating down the ramp at A, but accelerating, I guess, in that direction at A. Substitution.
Weight is mg.
All right, so I now have mg sine theta minus the friction is equal to ma, and mg cosine theta minus y equals 0. At this point, let's let the friction be 0. And so this now becomes mg sine theta. And therefore acceleration is now in the lab, when I ask you to find acceleration, what I want you to use the experimental value, don't use this formula. But the force that is trying to drive the box down the ramp, that's the mg sine theta. That is the net force down the ramp. So if you put a force sensor down ramp of this box, the value it should show should be, well, the negative direction because it's up, but it should be that magnitude. So in the lab, when I ask you what is the theoretical force down the ramp, I believe was the wording, or theoretical net force, mg sine theta is the theoretical net force. Then I asked, what's the theoretical normal force? Well, we got a formula right here. Theoretically, the normal force is equal to mg cosine theta.
So we just plug our numbers into those equations?
To get the theoretical values, yes. And then the question that asks about the coefficient of rolling friction, this is based upon the fact that there's gonna be a discrepancy here between the force down the ramp and your actual acceleration, which should be, basically, friction should account for that discrepancy. All right, questions to here, because we're about to bring friction into it. All right, I'm now about to reveal a formula that's been around since the late 1700s. And it really hasn't changed.
So we're not solving?
Well, oh, that's right. We can do that. So this becomes 9.8 times the sine of 53 degrees, which puts it
7.81, or 7.82.
I'm not buying that. I think you're in radians.
7.3. 7.826.
9.8 times the sine of 53 degrees is 7.8.
I apologize. I know where my mistake was. 7.93.
83, but, well, no.
No, 7.83.
No, 9.
7.8.
Meters per second squared.
Sorry for accusing you of the radian thing.
So what's the point of the other equation?
That's gonna go when we start talking about friction. Right. What causes friction? Besides demons.
Is it the surface of the material?
All right, so that is part of it, well, actually, correct you on one thing there. Say it again, just make sure that it,
The surface? Depends on the material of the,
plural.
sorry,
Surfaces,
surfaces?
yes, because the friction, if you look up the surface impact, it always gives you two objects, which two objects are rubbing against each other, because it does vary from combination to combination. So it does depend upon the surfaces. And that's bundled in this thing called the coefficient of friction. We will differentiate, but I don't want to differentiate quite yet. Most textbooks will break it down into two different types of coefficient, and most sources, if you look up, type in coefficient of friction, it will give you two types. So you want to keep that stuff. All right, so let's take surfaces here. So I have a box, I push on it, and it stops. If Newton is correct, and we assume that he is, after I let go of the box, did the box accelerate?
Yeah, let's accelerate.
Okay? Since the box accelerated, there must be a net force acting on it. What would have happened if it did not accelerate after I let go?
Motion.
Yeah, it'll keep doing whatever it was doing. So I push on it, it stops. Now, I add a kilogram, and now I push on it. Let's assume that I can match the exact same amount of force on it, or get it up to the same speed. Will it stop sooner, later, or the same? Good. I thought I heard something else, all right. And it does seem to stop sooner. So what I've done is there's more friction now between the box and the table. The surfaces have not changed, but what did change?
The weight, like, forcing each other.
No, weight did not. The weight of the box is still the same. The box did not change.
Like the weight effect of them pressing down on the table.
The
Force.
Pardon?
The force.
That's it. These are not the droids you're looking for.
Are they inversely related? When mass increases, acceleration decreases?
If the force is the same. But I'm contending that the force between, the friction force increased here. What actually did change? Max, you're getting close, but it's not the weight.
It's the mass.
The mass of the box hasn't changed either.
Acceleration.
Well, yes, but trying to get to friction. Do we need to do box on table again? Box sliding on table?
Normal force.
Normal force is the force that is registering how much they're pressed against each other. The normal force between the table and the box has changed. The weight of the box hasn't changed, the mass of the box hasn't changed, because this is not part of the box, this is a separate item. Normal force has changed. These are the two things established in the, I believe, 1790s, somewhere in there, that go into friction. So we have two types of friction here, maybe. That's one textbook. No, actually, let's get into the two models. The Nook and Cranny model. And I think I'm the only person who also built it. So if you type in Nook and Cranny model of friction, I doubt you'll get one. And then the attraction model. So if I have, say, object on table, if we zoom in, basically we've got, look at nooks and crannies on one object, and then we have ones on other objects. With a greater normal force, it's like two interlocking pieces here. With greater normal force, they're pressed in even tighter with each other, and it's a lot harder to move. Zooming in on this model, this is actually a whole bunch of little normal forces, sideways normal forces causing the friction. And in this model, once you get it moving, it's a lot easier for something to move over the top than it is if it's sort of wedged in there. And so once you get something moving, it's much easier to keep it moving. So if we look at friction and applied force just being whatever is trying to get it to move. Well, friction's going to match it. So as I push on this table right here, it's not sliding, but it is resisting me. I push harder, there's more resistance. I push harder, there's more resistance. At some point, I hit a breaking point. So the friction is always going to, if something's not moving, friction is always going to be enough to keep it from moving until you hit that breaking point. So the friction will match the applied force up to a certain point. At that point, it breaks away and the friction drops off to something else. This right here is this is kinetic friction here. F sub K. Kinetic friction. And that's equal to that coefficient times the normal force. The coefficient of kinetic friction. But the force that was front resisting before it started moving, that is known as static friction. And this peak right here is the maximum static, Fs max. So static friction, Fs, static friction, is less than or equal to Usy. And that less than part of it is because static friction is going to keep it in place until you hit that breaking point. So maximum static is Usy. Now, the attraction model. The Nook and Cranny model is sort of a repulsion. It's one object trying to prevent the other object from going through it. The attraction model is that the atoms, there's actually at the atomic level, there's an attraction between the two surfaces. And so if you zoom in, there's this attraction between them. And the greater the normal force, the closer the surfaces are together, and so you get a greater attraction. There's still this issue now, or there's now this issue of if it's attraction and not this, once you get it moving, why is it easier to keep it moving? Isn't the attraction the same? Because there's certain closeness together. You have a normal force pressing them together. The normal force isn't changing as it moves. Shouldn't the coefficients actually be the same? And there are two schools of thought on that. So if we look at friction and F applied, the first professor I ever heard talk to me about this said there's actually, what you should see is that. It doesn't drop down. That the coefficient of kinetic friction and coefficient of static friction, the error bars are so large there that you really cannot legitimately differentiate them. And so friction is less than or equal to mu y. Your textbook talks about the attraction model, but still differentiates between static and kinetic. And I tried to find somebody who had actually done really detailed experiments on this to see whether this shows up or that shows up. Because it seems like those are very clearly different predictions. And all I could find was a physics major's senior thesis where he did an experiment with error bars. And I mean, there was overlap there, but it wasn't, he didn't do like a million trials or anything like that. So, it comes into my head of why? Why do we not know? And my theory is because physicists don't care and engineers have something that works. When I say physicists don't care, it's because physicists, when they do their research, rarely are dealing with friction. Friction is primarily an engineering thing. Friction definitely was not a factor in any of the graduate work I did. I don't know if you dealt with friction, if you dealt with more applied physics.
No.
So, and engineers are very practical as a group, and so, you know, it works. And this differentiation works, so yeah, let's just keep doing it. There's a group at NC State that is trying to see if they can come up with a fresh approach on friction, but I don't know if they have or not. All right, so questions about friction at the moment? All right, so let's see, we've got the equations right there. Let us assume, let's see, I need to get rid of something here. So for the box on RAM, assume it will slide. In other words, I'm saying we don't need to worry about static right now. We'll deal with static in a moment. And so mu sub k is equal, let it equal to 0.3. Our force diagram doesn't change because we included friction in the force diagram. Their equations of motion to here, actually to here, don't change because it changes when we get to this point. Because we have a formula for friction. So this is the other next substitution. Since it is sliding, this becomes mg sine theta minus mu k y is equal to ma, and then y equals mg cosine theta. And solving for acceleration, well, we just take this right there and substitute it for y. So I have mg sine theta minus minus mu k mg cosine theta equals m. Every term has mass in it, so if I divide by mass, they cancel, and then they cancel with that. And so my acceleration is g sine theta minus mu k g cosine theta. So this becomes 9.8 times sine of 53 degrees minus 0.3 times 9.8 times the cosine of 53 degrees. And so somewhere around 5.2.
Got, you round it up, 6.1.
Man, my math is just really off today.
After making
That's right.
meters per second squared.
I will tell you, if you get an answer bigger than 9.8 meters per second squared, there's a mistake somewhere. Because that's free fall. So we talked about the fact that if it slides, it's kinetic friction. If it doesn't slide, it's static friction. But what happens if it rolls? Well, if it rolls, it's rolling friction, which is one of the questions on the lab. And so instead of mu sub k, it's mu sub r. Rolling friction is just a combination of the two, static and kinetic, because as a wheel slides, sometimes it rubs, sometimes it stays still. It's sort of a catch-all. Seems like some textbooks just ignore it completely. All right, questions to hear before I change the problem slightly? All right, let's change it slightly. Initial speed is 0 meters per second. U sub s equals 0.8. What is the acceleration? Our force diagram doesn't change. These equations don't change. That doesn't change. But what does change is at this point. The first thing we need to do is establish, is it going to move? So to establish whether it's gonna move, we have to figure out what is the breaking point, what is the maximum static friction? And so we just plug in the formula for the maximum static friction. That's now an S. That is an S. This is now 0.8. And now what do you get? Yes, I realize I do have the luxury of being able to erase on the board. Here's the tricky question. Therefore, what's the acceleration of the box? It is not. It'd be way too easy. Why is it not 3.1?
Because it's not moving.
Say it again?
Because it's not moving.
Oh, whoa. Almost there.
Did it overcome the static friction?
Did it overcome the static friction? Or change it around. It did overcome the static friction. Why? How can we look at that answer and know it overcame the static friction?
It's a positive answer.
Because the acceleration that we calculated beforehand is greater than that?
No, not. I think someone else said it though.
Because it's a positive answer.
Yes. This is the force trying to take it down the ramp. This is the maximum static. We got a positive answer. We overcame it. Once we establish that we have overcome the static friction, we now know it's sliding. And what was the acceleration when it was sliding? We just did the problem.
6.1 meters per second squared.
So that's the acceleration. First thing we need to do is establish, is it sliding or not? Once we establish it slides, then we do the sliding problem. We just happen to do the sliding problem first. Let's change it slightly again. Although I don't think this is a realistic number. I've never seen a coefficient bigger than 1, but we're going to make it bigger than 1. Let's make it 2.0. Now what is when we work through the math here, what do we get?
Negative answer.
Well, it's specifically negative what?
Negative 51.
Negative 51.
Yeah, I'm not even doing something wrong.
Good. No, my math's been off, that seems big. Because this was about 8.
Negative 6.6.
Negative 6.6? That would make more sense. Anyone want to back him up on that? Trust but verify. Negative 6.6, so what you're going to see. Or what are you getting?
Negative 3.9.
That's what I.
Yeah.
Oh, I forgot.
3.9.
I forgot the second 9.8.
Thanks for verifying. All right, so therefore, what is the acceleration of the box?
0. 0.
The whole thing?
0 meters per second squared.
Yes. Because we have not overcome the maximum static, therefore it is not moving at all. There is a physical reality to what we are trying to do here. If this were a legitimate answer, this means that I put a box on a ramp and it starts accelerating upwards, which would be really cool if it didn't violate all sorts of laws of physics. Nobel Prize and destruction of humanity. As a student, I always hated these problems. Because first thing you do is you solve for it's static. Get a positive answer, okay, it's sliding, so now let's do the problem again. I always felt like I'm doing the problem twice. And yes, you are doing a problem twice. If you keep the letters in until the last possible moment, don't make the substitution, at least you don't have to repeat that part again. Questions to hear?
When you were a physics student, how did you study?
Inefficiently. I didn't have old tests, not like I could go online and look at anything. I basically had the textbook and notes. So my method of studying was to look at the textbook again.
Reread?
Sure, we'll call it reading. It didn't fully click till after I was done with the class. So part of what I'm doing is the areas where I'm going, how could I have not seen that when the first time I went through the course? I'm trying to emphasize those areas so that you don't fall in the same traps I did. I got a B. Basically the equivalent of this course in the next one. All right. We got plenty of time. Let's see. So at least we can set up for the next one. Let's see. So mass of A equals 5 kilograms. Mass of B equals, let's make it 8 kilograms. Let's make this a 40-degree angle. We'll make this one a 50-degree angle. Friction on this side will make 0, and friction on this side will make static friction equal to 0.5 and kinetic friction equal to 0.3. Problem that potentially you're going to solve 3 times. Because we run into an issue very quickly. Force diagram, we got A here, we have B here. So we have the weight of A, we have tension acting up the ramp, we have normal force on A. Over here, we have normal force on B, we have the weight of B, we have tension acting up the ramp.
You say mu equals 0 here?
Yeah, for this side. I'm making this side frictionless and this side has friction.
Oh, okay.
Which way does friction act on mass A? Y, I see some fingers pointing. The velocity, you, I think we're advocate, the friction's acting down the ramp on mass A.
Yes,
Why?
because it's being pulled up.
How do you know?
Because the weight of V is greater than the weight of A.
Except the angle's not as steep. I mean, if I take it to more of an extreme of 90 degrees and 0 degrees, make that 1 kilogram, and make that 100 kilograms. Yeah, this weighs more, but this thing is not gonna be, this is not gonna be moving up.
Then I retract my statement. I said, then I retract my statement.
You might be right, but on a problem like this, you cannot necessarily immediately tell. Now, at some point, you might develop an intuitive sense, but at this point, you don't necessarily have that. So the first step is you guess. And you ignore friction. This thing's gonna go one way or the other, so if we start out ignoring friction completely, that should be able to tell us which way it wants to go, and then we can throw friction into it. So which way do you want to assume it's gonna go?
Against the box.
Against the box?
Oh, yeah.
So,
Or down the
but,
ramp.
so you assume A is gonna go down the ramp?
Yeah.
Okay.
Friction of it.
So we're gonna assume acceleration is this way and therefore that way. Don't know if it's right or not, but we just assume it. And that is where we'll leave off. Test Thursday, and then Tuesday we will pick up on this. You should be able to do most of master set 5. So although test is higher priority, but you know, what are you gonna do when the test is over? You start working on the master set 5, 6 concepts. I think it's 5, 6 concepts and 5, 6 applications. You can do some of both at this point.
So there are few master steps?
Sorry?
There are few master steps?
Yeah, yes. You're at the point where you can start working on those.
What do you assume the acceleration of your bigger weight is V, not L?
But the angles aren't the same. This is gonna have more of its weight acting down the ramp, but this is,
Decomposition.
and that's what I'm heading towards. There are some shortcuts that you can take. I mean, at some point, you can look at that and go, oh, here, hand me a calculator, okay, I know which way it's gonna go. But you're not there yet.
This is for direct test also,
No, this is not, all the fourth stuff is for the second test.
or you call that. What about those, the boxes and all that?
That's for the second test.
What is for the first instead?
Motion, position, velocity, acceleration. If you look at the old tests that I have posted online,
I have it, I put it already all in the computer and start seeing a little bit of that.
so anything marked test 1A is what you're having on Thursday. Anything that's marked test 1 will have a combination of some of the stuff that's for the first test and some of the stuff that's for the second
Yeah,
test.
so we write that right on there. I haven't even touched it.
Then let me see what I want to.
Did you take a picture?